The semantics of logic, in other words, the meanings of propositional sentences, is similar to the semantics of algebra. Algebra is unconcerned with the real-world significance of variables like x. What is interesting is the relationship between those variables expressed in our equations, and algebraic methods are designed to respect these relationships, no matter what meanings or values are assigned to the constituent variables. In a similar way, logic is unconcerned with what sentences say about the world being described. What is interesting from a logical point of view is the relationship between the truth values of simple sentences and the truth values of compound sentences within which the simple sentences are contained. Moreover, logical reasoning methods are designed to work no matter what meanings or values are assigned to the proposition constants used in sentences. Although logic does not prescribe inherent values for proposition constants, in analyzing logic it's useful to consider the values that logic users associate with proposition constants. Such associations are often called truth assignments. Formally, a truth assignment for propositional logic is a mapping assigning a truth value to each of the simple sentences in the language. In what follows, we use the symbol 1 as a synonym for true and 0 as a synonym for false. We refer to the truth value assigned to a propositional sentence using a truth assignment I by superscripting the sentence with I as the superscript. The assignment shown here is an example for the case of a logical language with just 3 proposition constants, namely P, Q, and R. P is assigned the value 1 for true, Q is assigned the value 0 for false, and R is assigned the value 1, again, for true. Note that the expressions written here are not themselves sentences in propositional logic. Propositional logic does not allow superscripts and does not use the equals symbol. Rather, these are informal meta-level statements about particular truth assignments. Although talking about propositional logic using a notation similar to propositional logic itself can sometimes be confusing, it allows us to convey meta information of this sort precisely and efficiently. To minimize the problems in this course, we use such meta notation infrequently and only when there is a little chance of confusion. A sentential truth assignment, as opposed to a propositional assignment, is an association between arbitrary sentences in a propositional language and the truth values 1 and 0. Unlike propositional truth assignments, sentential truth assignments are not arbitrary. Given a truth assignment for the proposition constants of a language, the semantics of logic fixes the truth assignment for all compound sentences in that language. Viewed another way, we can extend any propositional truth assignment to a sentential truth assignment by using the semantics of the logical operators in our sentences. Let's start with negation. If the truth value of a sentence is true in a truth assignment, then the truth value of its negation must be false. If the truth value of a sentence is false, then the truth value of its negation must be true. For example, if the truth value of P is 0, then the truth value of its negation is 1. If the truth value of a conjunction is 1, then the truth value of the negation of that conjunction must be 0. The truth value of a conjunction is true under a truth assignment if and only if the truth values of its conjuncts are both true. Otherwise, the truth value is false. The truth value of a disjunction is true if and only if the truth value of at least one of its disjuncts is true. Otherwise, the truth value is false. The type of disjunction here is called inclusive or, which says that a disjunction is true if at least one of its disjuncts is true. This contrasts with exclusive or, which says that a disjunction is true if only an odd number of its disjuncts is true. What about implication and reduction? These two are not quite so obvious as negation, conjunction, and disjunction. And in fact, in some variants of propositional logic, these operators are defined in different ways. The version given here is called material implication. The truth value of an implication is true if and only if its antecedent is false or if its conclusion is true. The case of reduction is analogous. The semantics deserves a few words of explanation. The intuition behind an implication is that the truth of the antecedent requires the truth of the consequent. So clearly, if the antecedent is true and the consequent is false, then the sentence as a whole must be false. This fixes the second row of the implication table. If the antecedent is true and the consequent is also true, then it makes sense to say that the implication is true. But what about the case when the antecedent is false? Such sentences are usually called counterfactuals. Intuitively, we might think that when the antecedent is false, an implication tells us nothing whatsoever about the consequent. Logicians have captured this, somewhat arbitrarily, by saying that the sentence as a whole is true whenever the antecedent is false, no matter whether the consequent is true or false. Some people find such counterfactuals disturbing. Consider the sentence, "If George Washington is alive, I am a billionaire." In the real world, this sentence is true, given our semantics, since George Washington is not alive. This feels wrong to some people because the antecedent seems to have nothing to do with the consequent. The good news is that, other than this slight oddity, everything works out very nicely with the semantics, as we shall see. Finally, we get to equivalence, and this is an easy case. An equivalence is defined to be true if and only if the truth values of its constituents agree. In other words, they are either both true or both false. Given a propositional truth assignment and these definitions for operators, we can compute the truth value of any sentence in the language. The technique is quite simple. We first replace the proposition constants in our sentence with their values in our truth assignment, forming an expression consisting of ones and zeros and logical operators. We use our operator semantics to evaluate sub-expressions with these truth values as arguments. We then repeat, working from the inside out until we have a value for the sentence as a whole. Here's a simple example. We start with a formula and a truth assignment for a language with 3 proposition constants. We replace the constants in the formula with their truth values. We replace the negation by its value, in this case, 1 or true. Next, we replace the 2 disjunctions with their values, both 1. Finally, we evaluate the conjunction to get a value for the entire sentence. Here's a more complex example. In this case, we are using propositional logic in digital circuit analysis. There are 3 input nodes, some internal nodes, and 2 output nodes. There are gates connecting these nodes to each other, 2 XOR gates shown at the top, 2 AND gates in the lower left, and an OR gate in the lower right. In our model, each node in the circuit corresponds to a distinct proposition constant. Using the language of logic in this vocabulary, we can capture the relationship between the values of the nodes as propositional sentences. For example, the output of the first AND gate is 1 if and only if the 2 inputs are 1. With this encoding, we can write a formula for the truth value of the second output of the overall circuit in terms of the truth values of the 3 inputs of the entire circuit. This formula then holds no matter what the inputs are. We can then use evaluation to simulate our circuit. First, we replace the proposition constants with their truth values. We simplify our negations. We simplify our basic conjunctions. We simplify one disjunction, the resulting conjunction, and the remaining disjunction to get a value of 1 for the sentence as a whole. This exercise tests your understanding of evaluation by asking you to determine the truth values of various sentences for a given truth assignment. Let's finish up our discussion of semantics with a few definitions for future use. We say that a truth assignment satisfies a sentence if and only if it assigns the value 1 to that sentence. A truth assignment falsifies a sentence if and only if it assigns the value 0 to the sentence. A truth assignment satisfies a set of sentences if and only if it satisfies every element of the set. And a truth assignment falsifies a set of sentences if and only if it falsifies at least one element in the set.